What I'm going to be doing is I'm going to discuss with you the synchronous motor, and the synchronous motor is a really interesting piece of equipment, and so I'm going to go over it in a fair bit of detail. And so what I want to start with is I want to just do a quick summary of the motors that you've already looked at, and then we're going to see how the synchronous motor is really different and really special in a lot of ways. Okay, so let me show you, we're going to look at the other motors that we've done, and I just want to summarize a few points. Let's take a look. All right, to begin with, the first motors that you've already looked at in a certain amount of detail are the squirrel cage induction motor, the wound rotor induction motor, and the split phase. And even though it's not in the name, it's also an induction motor. All three of these motors operate on the principle that you have a revolving field in the stator windings, and that induces voltage in the rotor. And these motors are all what we call asynchronous, which means that the field is rotating at a synchronous speed, but the actual rotors at full load slip. Now, some of them slip more than others. Wound rotor motors can operate at up to 20-25% slip, while most squirrel cage motors are maybe in around 2.5 to 3%. And single phase motors sometimes a little higher, maybe 3 or 4%. So but the idea is that if the motor did not slip, like if the rotor didn't slip behind the revolving field, then there would be no rotor frequency. And if there's no rotor frequency, there would be no voltage, no current, no flux, and therefore we would not have the interaction of rotor flux and stator flux, which produces torque. So the torque of each of these three motors behind me is actually dependent on the fact that we have slip. Okay, so slip is actually critical for the operation. Now, all three of these motors take an electrical input, so their input is electrical energy, and they put out torque, okay, horsepower. The output is torque, and that's pretty much, with maybe some few exceptions, that is the case for all three of these categories of motors. The idea is we supply them with electrical energy, and what do they do for us? They put out torque. And when it comes to the synchronous motor, we say synchronous motor, it's actually a synchronous machine. It actually has more than one function, and so I'm going to start to do a little bit of a diagram, and I'm going to start to show you what it is exactly that we do with the synchronous machine. So I've done a little bit of a drawing for you, and let's take a look. First of all, this represents essentially the frame of the motor, and around the outside, in exactly the same way as that you have in a squirrel cage induction motor, there's stator iron around here, and it would really be kind of like this. There would be slots like this of iron that would go down and up like this. And I didn't draw them all in. I didn't want to confuse the drawing too much, but this would be the stator iron, and we have windings that are wound onto those. Now, the windings in a synchronous machine are done just a little bit differently. They are wound in such a way that as the poles, remember there's a three-phase power supply connected to these stator windings. These are the windings right here. These are the coils. There's 12 of them here, and they're wound so that as the currents rise and fall, it gives us revolving magnets, and they're alternating north and south. So in other words, I've basically put I've shown the magnets in these little blue boxes just behind the winding. So if this one is a south, north, south, north, south, and so on. Now the thing that you need to really clearly understand is that the winding itself is, of course, fixed in position. But when you apply three-phase voltage to it, these little magnets, and I've shown some little speed lines there so you can see where they're going, these magnets are going around, chasing each other around, in this case, at 1800 revolutions per minute. Now, if I have 12 actual coils, 12 stator coils, it's a three-phase, that means 4 poles per phase, and so what that is going to give us, of course, is we know from our synchronous speed formula, that's going to give us 1800 RPM. So the 12 actual poles translates to 4 poles per phase, and so we call it a 4-pole motor actually. When we say a 4-pole motor, we're talking about 4 poles per phase. So this is a 4-pole motor. It will have a synchronous speed of 1800 RPM. Now, the thing that's different about this motor, that really sets it apart, is the way that the rotor is designed. Now, what I want to show you is this. This is called a salient pole rotor. There's a couple different kinds, but this is the most common one. These are usually used for a little bit slower speeds. And what they have is they have some little bars, essentially, poles that actually stick out, okay, all the way around. Now there's the same number of these chunks of iron sticking out all the way around the rotor as there are stator coils, exactly the same number. And to make things even more interesting, they've taken the entire rotor and we create an electromagnet with it. So what we need to do to make an electromagnet is we have to first of all have a coil of wire, and secondly we have to energize it with DC. So what that means is this rotating part is going to have DC voltage and DC current in this winding. Now this is called the field winding, and it's one long coil wound in series, and the segments are wound so that if this is a north pole, this is a south, north, south, north, south. Now the interesting thing is that matches to the way that the stator windings are wound. So that means that when we do energize this stator, we're going to have the same number of sort of alternating north-south poles here as we do here. And we're going to get into this in quite a bit more detail, but the end of the story is that this north pole here would lock onto this south pole, and this north pole would lock onto this south pole, and that locking action goes on all the way around, and so the rotor actually spins at exactly the same speed as the revolving field, and that's why it's called a synchronous motor. Its rotor speed is synchronous, okay? Constant speed motor. Now, just a few things about the way this is done. If we have a rotating field here, how do we get DC voltage in there? That's one of the questions that comes up pretty early. Now, there's two ways we can do it. We can either on the rotor shaft we can put 2 slip rings. Now the reason we want slip rings is that way we can have an external DC source. So we can have a DC source here, like this, and it would just go in through a couple slip rings, and it would appear in here, and then it would just go around through all of those windings. Okay, now that's one way to do it, an external DC source and slip rings. The second way to do it is to actually put, they call it an onboard exciter, and what they do is they actually, on the end of the shaft, they set up an AC generator, okay, so that it actually generates voltage on that shaft as it turns, and then they rectify that voltage to DC, and feed that DC into the field. But that whole rectifier with the generator hookup that then supplies this field, there's actually no connection. It's brushless essentially. So that's another way to do it. Okay, so there's a couple of different methods, but the bottom line is, here's what we have to have. We have to have a DC voltage that we can run through these windings to make field poles. Okay, and they're fixed polarity poles. And so we have to be able to do, there's a couple of things we need out of that. We need to be able to turn it on and off remotely, and we need to be able to vary the amount of current flowing. So if we had an external source, let me just make this look a little neater. If we had an external source right here, I'm going to put this as my negative and my positive. We would need, first of all, a switch. Okay, we got to have a switch so that we can shut the field current off. And secondly, we need to be able to control the value of it, so we have a field rheostat. And so this is what you would kind of see, is something like this. Now those two lines would go down, behind onto the slip rings, and then essentially bring that voltage into my rotor. So we need a DC source to give us field voltage and field current that will produce these permanent magnet, these electromagnets, but fixed polarity magnets on the actual rotor. And then of course, I didn't draw it in, but we know that we need this. We have T1, 2, and 3. So we have to have a three-phase source of voltage to supply the stator. And so two sources really needed in order to make this work. A three-phase AC source and a DC source to supply energy for the field. Now, I'm going to reconfigure this drawing just a little bit, and I'm going to start to show you some of the other interesting details. There are a couple of things that you need to know for sure. This motor has to be started with the field. In other words, that electromagnet has to be de-energized, has to be off. And I'll show you why. What you need to do first of all is energize your stator windings. And that means that we will now have a revolving field in this motor of 1800 RPM. Now, the rotor itself is at zero RPM. And if you think now about the theory of this, if I were to energize this motor at this exact instant with this at 0 and this at 1800, we're expecting that we're going to get this magnet to lock onto this magnet. Well, to be honest with you, this is a little bit of a difficult thing, and it's a little bit like the example I like to use. It's a little bit like merging. If you have through traffic that's that's at a speed of 120 kilometers an hour, and if you come in from the side at about 100, 110, normally somebody will leave you a little space, or you can make your own space, or something happens and you kind of make your way into the traffic, and it works out pretty well. But if you come in on the on-ramp at about 20 or 30K, and you start trying to to see if you can find a way into that 120K traffic, is going to be a problem. And this motor is no different. In other words, the speed of the rotor has to be real close to 1800 RPM before you can actually energize the windings that make those rotor magnets. So, but let me show you just what would happen if you tried, okay? Let's say that we energized this and this magnet became a south. And what I want you to see is this. This is going at 1800 and this is at exact 0. So that means that for a brief instant in time, this magnet right here is in line. But a fraction of a second later, it would be over here, right? And that means that this north would tend to pull, it would tend to create a little bit of torque in this direction as it moves here. But then what happens is, and at the same time essentially, this south would be kind of pushing on this one, and so there would be a little bit of torque in that direction. But when this south gets to here, to the point where this north area is right now, this south would quickly be here, and then this south would move sort of into this position, and all of a sudden we would be producing a torque in this direction. So there's kind of this, because of the huge speed difference, we produce, because of the fast moving field, we produce some torque on the rotor this way, and then this way, and this way, and this way. And it basically winds up being about the same amount of torque in each direction. And the motor wants to work. But all it does in that case is you have this conflicting torque, and you'll hear the actual motor, and it'll kind of make a grinding noise. And it's not going to go. The rotor can't go anywhere because it has the same amount of torque acting on it in both directions at the same time. So nothing happens, okay? It's not going to start. And so we know that that is not going to work. So we go, all right. We don't have, this is not a squirrel cage motor, okay? So we don't have any, there's no rotor bars in there really. All we have is this iron in the rotor, and we know we have all these field windings on here, field windings that are all wrapped around these. So we go, how are we going to do this? Now originally, when the motor was first designed, what they did was they would do this. Here was your synchronous motor with your output shaft. And what they would do is they would belt up onto here to some other type of motor. Maybe it would be a tractor, maybe it would be like a diesel or a gas engine, who knows, something like that. And they would start this motor up, and they would run, and they would actually spin this rotor. And once they got this rotor up to about 95% of synchronous speed, once you're at about 95%, then you could energize these, and now the speed difference between this field at 1800, you know, these would be going like this as it went, just a little bit faster as it went around. But if you energized that, there was enough strength in the flux that it would boom, and it would lock on. And we call that pull-in torque. Pull-in torque is the point where when you energize the field, it can establish a flux link. And let me just show you, I'm going to erase a little bit here and show you what that flux linkage looks like, okay? It actually looks like this. Let me just get rid of these magnets right here. I'll sacrifice those just so we can look at what this does. And the flux linkages go like this. This is going to be, if we energize this, this is going to be south, north, south, north, south, right? And here's what the flux does. So remember, this has to be going at least 95% of the speed of the field. Now, we close the switch in the DC, and these poles appear. And the flux goes like this. This south flux flanges up to here, goes around. Now remember, this is a south pole right now, so the flux goes like this, and it comes in, and it forms a loop right there. Now from this same magnet right here, this north flux goes this way. This is actually a north pole, comes from here into this south pole, and forms a link there. Now this south pole, this north has flux coming this way, goes into this pole, and comes out like that. Now this one comes like this, and goes like that. And so you have linkages, we call these flux linkages, and they hold all the way around. And so what happens, and flux is amazingly powerful, very, very strong. So once you initiate the current in your field winding, and these magnets appear. As long as your speed is close enough, they go ka-chunk, and they form these linkages, and now that thing is synchronized. We call it synchronized. And now the rotor is going to go the same speed as the revolving field. And then what they would do is they would take that pony motor and, they'd have some kind of a clutch or they disconnect it in some way. So the pony motor, as it was called, a pony motor would be used just to start the rotor spinning so that they could synchronize it, and then you didn't have to have that pony motor anymore, and it operated just fine. Now, as time went by, they started thinking about things like, how could we get these motors so that we could start them without having to have a pony motor? Now, an interesting thing for you to note is that even now, large synchronous motors, even though there's a couple other techniques for starting synchronous motors now, pony motors are still used on really large synchronous motors. So, it's a combination of methods, but the idea of a pony motor especially on a very heavy load, like a really large synchronous motor, the idea of having a pony motor is still something that happens, all right? But let's look and see what they did. They said there's got to be a way to start at least some of the smaller ones without having a pony motor. And so here's what they did. Now I'm gonna take this pony motor away. What I want you to note though is that this 95% is important either way. We have to be at about 95% of synchronous speed before we can close the switch and create our rotor magnets. So what they did, and I'm going to draw a couple of, I'm going to just clean this up a little bit. I want to show you what they actually came up with. Kind of interesting. So in this surface right here, I'm not going to draw too many. I'll just put about 3 on each one maybe. Now we have holes that are bored lengthwise all the way through these. And let me show you a little bit of a different view of it. Imagine this here, and I'm going to show you just a little different perspective of it. Okay, imagine that we're looking at this piece here, and this is the actual part that's sticking out, okay? So around here, this is really this piece right here, just from a different angle, okay? Now imagine that we had this, and these went down to this end, and then we slid some copper bars through there, some copper wires, and we soldered them together up there and down here. Now what would we have? What does that look an awful lot like? That looks a little bit like a rotor bar, doesn't it? And so what happens is, in fact, by taking and inserting these bars just in the surface of each of those, we create what I'm going to call, for now, I'm just going to call it a light-duty squirrel cage winding. And its first purpose that I'm going to discuss with you is actually starting the motor. So here's what happens. Now remember, this pole is this piece right here. So this is actually where the windings go around here, right? All the field windings go around here because this is what we want to turn into, for instance, a south or a north pole. But let me now take you back, and I'm going to clean this up a little bit. And I'm going to take you back, and we're going to start again, and I'm going to show you what they do. So imagine here, there's the stator windings, right? Here are the revolving magnets. Basically, these are fields of flux that create a magnetic pull, okay? These are invisible moving magnets. I'll make this one north, south, north, south, and north. Now they're moving around in the iron. Now imagine this. I've got a pole here, a pole here, a pole here, and here. But remember, because I'm starting at 0 RPM, I can't energize the field switch yet. So even though I have these revolving magnets, I cannot energize these yet because I know it'll just grind because their speed difference is too great. And so here's what happens. Because I have these light duty squirrel cage windings in here that are actually embedded right there, now what happens, and this goes back to your your squirrel cage induction motor theory, is that now I have flux cutting across conductors that are shorted together and make a circuit. And so that means I'm going to have a little bit of voltage and a little bit of current and some flux. And that flux is going to interact with this flux, and it's going to create torque, and it's going to start that rotor turning. Now what you really need to understand about this is a very light duty amount of torque. And so synchronous motors are always started with no load. If you try and start this with load on it, the current in your rotor is going to shoot up like in these little bars, and these little bars are going to melt out of there. So what you have to do is you have to start it with no load. So no load and your field switch open. And then what happens is you should be able to get your rotor turning, your rotor speeds up. Now remember, as the rotor goes faster and faster, it'll get up to 95, 97, 98%. Remember, it's not uncommon for induction motors to have a no load speed that's only 0.25% less than its synchronous speed. So honestly, as long as there's no load on the motor, not a problem. You should be able to get it up there. So as soon as you're up close to speed, you close the switch, and these turn into, in this case, south, north, south, north, and south. Now, our flux linkages develop, right? Our flux linkages develop around these magnets like this. Everyone has links on it. And as soon as that happens, now the rotor is going a full 1800 RPM. And at that point, now we need to stop and we need to think about these bars. If the rotor is going 1800 RPM, how much rotor frequency do we have in those light little bars that we used for starting the motor? Well, it's 0 because the rotor is going the same speed as the field. There is absolutely no flux cutting bar action, and so we know there's no voltage, no current, and no flux. And so that means that in terms of a squirrel cage type motor, where we need some slip to create torque, this thing is now at that point where the rotor is going the same speed. And so we would think, okay, there's no way that those bars can be producing any torque. And we're right, okay? Those bars at this point, as long as the rotor is going the same speed as the field, there is no torque being created by anything from those little bars. Now, those bars actually have a name, and they are called the amortisor winding. Amortisor winding. I'm not sure if that's the right spelling, but it's got to be close. Amortisor winding. Okay, and the amortisor winding has a couple of important jobs. I've just described the first one to you. So the first thing that the amortisor winding is there to do, it's like a light duty squirrel cage, and it's there to start the rotor and bring it up to speed. Once we can close the field switch, energize our electromagnets, and synchronize the rotor to the field, then those bars now don't really have anything to do, okay? So I'm going to reconfigure this, and we're going to look at what its second purpose is. So the next thing that we want to look at is important feature, question that's going to come up. How does this motor actually produce torque? And we know, with the asynchronous motors, the torque comes from the fact that we have slip, and that slip means we have rotor frequency, and that of course gives us voltage, current, flux, and that creates torque. But in this motor, rotor's going the same speed, and so there's got to be something very different going on here. Now let me explain it like this. What I'm showing you here is these magnets that I've shown here. These are the revolving magnets, okay? These are the revolving field magnets right here. And this part here is the actual salient pole on the rotor, okay? And what I've shown is the flux linkages. Now, when this motor has essentially no load on it, the alignment of this north pole to this south pole will be almost perfectly straight. In other words, you could draw a center line through there and it would be about even on both this flux field pole that's moving and this actual rotor pole. That flux would be pretty much in the center. And these flux linkages would look like this. They would be quite a uniform shape, a little bit like a grapefruit segment, okay? Now, what happens is that this is the output shaft. And so we have the field going this way, the rotor going the same direction because it's locked to the field. And now, if we place mechanical load, in other words, let's say this shaft is driving a big grinder, but there's nothing in it. And now, you're going to be chipping trees up, okay? So the front end loader comes along, grabs some trees, drops them into the hopper that's feeding into this grinder. Well, guess what? If the rotor is going this way, those trees, as they enter into the chipper, are going to produce a counter torque that's going to try and slow this motor down. So the counter torque will be in this direction. And we know that as we physically place mechanical load on a motor, they slow down. They try to slow down. Now we've already said that this motor it runs at a constant speed. So we're kind of going, well, it can't slow down. But let me show you what happens, and this is very, very interesting. When you place load on this motor, the counter torque does this. It takes this rotor shaft, and the shaft is trying to be, the counter torque is pushing back this way, and look at what happens to the flux. Now, instead of the flux being straight, the relationship of the rotor to the revolving magnets of the field actually changes. Here they're even. Here the rotor is being twisted backward because of counter torque. So it's being stretched backward. Now, the more load that you put, the more counter torque, the further back it will stretch. And once you get it up to a certain amount of load, as long as it's within its rated capabilities, it'll just run like that. Still at the same speed because it's still locked on to the revolving field, but the flux linkages, each one of these flux linkages will be stretched. And if you look at the shape of this, because it has to flow through the iron, right? And so the flux gets stretched. And interestingly enough, when flux gets stretched, it actually, it's like a band that produces a pull, a constant pull, trying to make its smallest loop. Flux always tries to make the smallest loop possible. It's elastic. It's just like rubber bands. And so over here, this is going to move back because of counter torque, and it's going to stretch the flux lines. And that is actually where the torque comes from. The torque in this motor comes from stretched flux linkages. So very, very interesting. the way this works. And what I'm actually going to do, I have a little something, a little interesting demo that I'm going to show you in just a couple of minutes. All right, this machine that you're just looking at here is a little bit of a model of a synchronous machine. And let me show you around a little bit. You can look at a few of the parts. And let me show you how it works. Now, this piece right here is represents the rotor. And as you can see, the rotor is free to turn, okay? So the rotor is free to spin. And this silver ring that goes around the outside represents the revolving field. So this north would be a north pole in the revolving field. This would be a south, north, south, north, south. And you can see that the rotor actually has, you know, these would be the poles on the rotor, those salient poles that I had mentioned. And so this would be the actual pole piece. And so when we energize this field winding, this would become a pole, this would become a pole, and so on all the way around. Now I have indicated on here also, as you can see right there, those 4 little dots, those represent the amortisor winding bars that would be installed in the poles on the rotor. Okay. Now, the thing that you have to imagine in order to see what's going on with this example is that this is a frozen frame of, you know, it's like taking this motor and freezing the revolving field and the rotor at exactly the same time and just being able to look at them like a freeze frame shot. Because here's what you need to think. The revolving field is rotating at 1800 RPM. And if we're going to successfully synchronize this motor, then this rotor has to be going at least, you know, probably 1780 or 1790 RPM, nice and close to 100%. And then we can actually throw the switch, create these magnets, and it will synchronize. And so what I'm going to show you is, so what we're looking at is really, imagine if this was just starting, you know, it would actually be going in this direction with respect to the rotating field. As this speeds up, the difference would become less and less. And at that point, we would say, okay, let's go ahead and synchronize this, okay? So what I'm going to do, I'm going to set this down, set this still, and I'm going to show you how this works. Now, in real life, in terms of visible objects, rubber bands are the closest thing that there are to represent flux. Rubber bands are exactly like flux. And so let me just show you this example. Here's what happens. If I take a rubber band, I've got several of them here, and I stretch them, I can hold it like this for a little while. But then what happens is, if you maintain that pull for a while, all of a sudden, it's a little bit like watching those guys in Oktoberfest doing those beer holding contests where they have to hold this vat of beer out at the end of arm's length. And after a while, you know, your arm starts to, your muscles start to tremble a little bit. Why is that? Well, it's because it takes an absolute constant torque to keep this band stretched. And so what happens is, in the synchronous motor, I showed you that when the load is placed onto the shaft, that the bands of flux, the flux linkages, which I'm placing right now these flux linkages have to stretch when we place load. And so when you actually stretch some flux lines out, they produce torque. They produce, in a very literal way, a constant pull. And so I'm just putting my flux linkages together like that. And I've got one more. And there you go. Now, what this represents is, at this point in time, we've thrown the switch, we've created these magnets, and now we've got a south locked onto a north locked onto a south, and so on, all the way around. So we have this outer ring traveling at 1800. We have the rotor traveling at 1800. Now, if I place load on the rotor shaft, here's what happens. This rotor goes like this. It moves backward, okay? Now, as I pull this back, look at the length of those flux linkages. The flux linkages actually get longer, and when they get longer, they stretch out, and that means that there is a constant torque produced which tries to shorten those linkages. And I'm going to show you what happens if I let go of this, just so you get an idea how much force there is there. Okay, so if I let go, it pulls it up right away. Now, when you load a synchronous motor, of course, you want to add the load in a very constant sort of a way. And so what happens is, you start adding load, the rotor moves back. And when you get to something like about this, something like that, there is an angle that they say, if you think of this flux like this, and then you think about twisting, putting load on it, stretch, now that flux is literally over here at an angle. When this angle moves from this as being 0 to about 60 degrees, that's about as far as it can stretch. And there is a limit. If you place too much load, what happens is these linkages all break. And we call that pull-out torque. It's the amount of torque that it takes to actually break the flux linkages. And if that happens, the motor will stall almost immediately. And the only way to get it started then will be to de-energize the field switch and remove all the load, and it'll be a real process. So in normal cases, you'll load this motor up, but you don't want to press it real hard right to the end. So, but a lot of torque produced by that stretched flux linkage all the way around. So now the south is not lined up completely with the north. It's actually back a little bit like that, and the flux is still holding on. This magnet's holding on to this magnet, but it's stretched back. Now think of this. Here at no load, we have our rotating field going around, and we have our rotor going around, and they're going exactly the same speed. So there is no flux cutting those windings there, because the relationship is exactly even. Now, once I've placed the load on and I stretch this back, now this is traveling exactly 1800 and this is traveling exactly 1800. And so there's no flux cutting those bars. But how did I get to this position? And this is very interesting. During the change, during the period of time as you add the load, where the rotor position stretches back, the flux stretches back to here, during that time, the rotor is actually, for a brief period of time, during that adjustment, the rotor is going slower than the revolving field. And think about it, if you're walking with somebody and all of a sudden they're walking the same speed as you but 10 meters behind you, something happened. They must have slowed down for a little bit. And so this is the same principle. So if this is back here, that means that this must have gone slower for a little bit of time. Now, this is so sensitive, these bars are so sensitive to that what happens is during the period of time while this is moving like this,
there will be some flux cutting those amortisseur winding bars during that period of time. And that flux, basically it will produce a voltage in those bars that will make some current and some flux, and the flux will produce torque that fights against the movement in the backward direction. So in other words, it will produce torque in the same direction as the rotor is going, like this. And once you reach this position, then this part stops, relationship's even, and there will be nothing in the bars. Now what happens if you take the load off quickly, and I showed you this, watch this. You can see that it actually oscillates. It doesn't just go like this to here, it actually pitches forward. Okay, so synchronous loads, synchronous motors typically do have some issues with oscillations. And so, because it's just like riding on a cushion of flux, like this. And so, what they do is, if the rotor is moving backwards, then with respect to the field, then these amortisseur winding bars produce flux that pushes the rotor forward. And if it pitches forward and the flux stretches the other way, then there'll be an induced voltage in these amortisseur windings that pushes back on the rotor. So in other words, instead of going like this, it will tend to go more like this. And it will come to a stop as soon as possible. Now, what we call that effect is a dampening effect. And so another name for the amortisseur winding is a dampening winding. And the word amortisseur itself is actually the French word for shock absorber. And so if you think about it, what are these windings doing? Well, when there are oscillations, in other words, changes, they basically dampen down that effect and they absorb the shock of the oscillation moving back and forth. So these amortisseur windings, this is their second job, is to act as a shock absorber to calm down the movement of the rotor with respect to the revolving field. Okay, so extremely interesting action. And I wish you could feel how hard this is to pull down. Once you get all those bands of flux on, it actually takes a lot of effort to keep it in this position. And that's the best way to understand that, you know what, if you place a load on that motor, as long as you have the load connected to the shaft and the motor's running, that counter torque is constant from the load, and this torque that's being produced by these stretched flux lines is just as constant, basically pushing back and delivering the torque against the counter torque of the load. So the stretched flux in a synchronous motor is what produces the actual torque. All right? Now, the next interesting thing that I just want to point out to you is that this angle right here, with no load, it's nice and straight, right? Nice and straight. At load, this angle changes. And this angle we call torque angle, okay? That's called torque angle. And torque angle in a synchronous motor is a result of the stretching flux. And so it's basically, if you add load, then the torque angle changes. If you reduce the load, then it comes back. So the only thing that affects the torque angle in this synchronous motor is actually the amount of actual load, counter torque, that you place on the rotor. That's the only thing that affects the torque angle. So this is looking at the inside of a synchronous motor, and this is an open design, so you can actually see in, and we can see the kind of the inner workings and the inner parts. Now, in this one, you're going to see that there are actually, see those two big wraps of wire that are inside there? And those are your Those are parts of the field coils. Now this is a lab machine, and it doesn't need very much torque. And so they've just actually wound the rotor with one north and one south pole. And that's why you only see 2 coils of wire on each side. So in a real application, this is actually a 4-pole synchronous motor, which means that there are 12 poles around the outside. So in these windings around here, there are actually 12 poles. But seeing as this rotor never really has to do any work, it's a very small motor, what they've done is they only place 2 poles on the rotor, and that's plenty to hold it into synchronization. Okay, so as a lab machine, there's a little bit of a variation here. And one thing interesting that you'll see is, I'm going to point it out to you here, right here is a heat shrink with a couple of wires, and those wires go to the field winding. So basically these two packs of wire are the 2 field pole windings, and they come into these wires right here, and then they go into a slot. I'll turn this so you can see it. They come up that slot underneath of the bearing, and then they come up and they solder onto these 2 slip rings. Now, how does the DC get in? Well, through these brushes right here contacting the slip ring. And so we have our external DC source. It comes in, goes in through the slip ring, and then basically onto the rotating part, which is the shaft, down through those wires and into the field windings. Okay, so you can see how that goes. Now look how close the actual air gap is between the stator iron, which you can see, it's the little wedges of iron that you can see in the bottom of the frame, and the actual surface of the rotor. Very, very close. And so the reason that air gap is maintained at a very close level like that is that, remember, the only thing that produces torque in this motor is the flux linkages. And so we want to make sure that air gap is pretty hard on flux. So we want to keep it really, really minimum in order to have to keep the flux linkages nice and strong. All right, now we're looking at the other end of the motor, and now we can see the other end of those windings, and of course, just next to the housing in here, those are the stator windings. Like I mentioned before, those will be wrapped in this motor with 12 poles, 4 per phase, making it a 4-pole motor that will revolve at 1800 RPM. Now, I'm going to just close the door, and I want to show you the connections. So here we have our supply down here, 120 volts DC. These 2 points are where we would supply our field current. And you can see that it comes in through this switch. This is the field switch. And then it comes up into these windings right here. That's our rotating field, our rotor poles. And that comes back down through this rheostat. This is to control the amount of field current, and then back down to our negative terminal. And on this side we have our stator leads. So this is where we supply the three-phase AC into these terminals just below here. All right, so it gives you a little bit of an idea. It's nice to see the machine and get a little bit of an idea what the real equipment looks like. The synchronous machine actually has 3 important applications. We've been talking about it as a motor,
And as a motor, we can see that the input is electrical energy and the output is mechanical torque. And the next application is just the reverse of that. We take this same machine, we hook it up to a prime mover, and we input torque from a prime mover, and we spin it at a very constant speed, and our output is AC three-phase electrical energy source, okay? Becomes a source. The third application is as a synchronous condenser or a capacitor. And what it does there is our input is voltage, and our output can actually be pretty much purely just leading VARs if we want. Now in many cases what happens is we get a large synchronous motor, much larger than the load that we need to operate, and so when then we run the motor it may be half of its mechanical output, so half of its horsepower rating, and the other half of its rating, which really is still quite a bit of current, we turn it into power factor correction for the rest of the area. You know, there may be an MCC with many other motors on it. So really interesting application. And these motors are typically in larger sizes. Now we just saw a clip of one in the lab, and obviously just a very small machine. But I want you to be aware that most synchronous machines range in the size between 200 horsepower and 20,000 horsepower. Okay, so these are typically very large machines and you know, heavy industrial applications. So what I'm going to do is we've already talked about the motor quite a bit. We're going to briefly talk about how it can be used as an alternator, and I'm going to also just briefly show you how it can be used as a capacitor. Now in order to really explain these two operations here, the best thing that we can do is to take a look at some vectors. So I'm going to draw a few diagrams, and then I'm going to show you how that works. So the vectors for this motor look a little bit like this. And first of all, let's just think about the stator windings. The stator windings, we know, are connected to the three-phase supply line. And so the first thing I've done is this blue line right here, I've called it E line. This is the applied voltage from the source being applied to the stator windings. Now, interestingly enough, what happens is, because the stator windings are fixed in position, as the rotor turns, and remember, it's locked onto the revolving field, and so the flux is passing, the flux of the magnets are passing by those windings, and they actually induce a voltage in the stator windings. And the angle of that voltage is almost, well, it would be exactly 180 degrees opposite from the line voltage, except for one thing. When you place load on the motor and the flux stretches, remember in our model that the flux stretched because the two magnets weren't in line. So the rotor magnet pulls over here and the actual field magnet is here, and it pulls like that. So now you have the flux passing at an angle past the windings. And so what happens is this induced voltage, which we call CEMF, is not actually produced at exactly a 180 degree angle. It's a different angle. And this right here, this difference, is the torque angle. So the more load we put, the higher this vector will move. The lower the load, it will come down. It'll never come right down to exactly 180, because even with a motor unloaded, it takes a little bit of effort. There's a little bit of counter torque, even from a motor with no load.
And so that means that this line would never come right all the way down. Now, this diagram, please realize I'm showing this motor with just a moderate load on it. And so the torque angle is somewhere, just in this area. And just realize, where does this voltage come from? Well, this voltage is created by the flux linkages passing by the stator windings as the rotor spins. So we have applied voltage and we have an induced counter EMF, both of those voltages inside the stator windings. An applied voltage and an induced voltage in the opposite direction, or very close to the opposite. Now, anytime that you have two voltages in the same winding, they basically work, the two of them together, and there's always a resultant voltage. And so the resultant voltage is simply the vectorial addition of these two voltages. Now, if we were to place more load, this would come up on an angle like this, and our triangle would be a little bit longer, and our net voltage would rise. If we moved this down, if we removed load, then we would have a long parallelogram at a shallow angle, and this voltage would come down. Now, the actual current drawn by the motor is determined by this voltage. It's the resultant voltage. And so the lower the load, this torque angle gets less, and our resultant voltage goes down, and of course our line current goes down. Now, these two values right here, the resultant voltage and the line current, basically this is the resultant voltage in a winding that has a highly inductive ratio, like very low resistance and very high reactance. And so, in fact, the current and this voltage are always pretty close to 90 degrees separated. And they move just like one piece, okay? So if this voltage changes its angle, this resultant voltage changes its angle, and the current changes its angle. Now, this is why this motor is so interesting, and what we can do is we can actually take it and adjust it so that it literally runs at unity power factor. Unity power factor. And so let me show you how we would do that. Now remember, this CEMF is caused by the flux linkages cutting across the physical stator windings. And so what we could do, and let me just show you this. I'm going to move this word over a little bit. This is the CEMF. If we were to take the field rheostat and reduce the resistance a little bit, what would happen is more current would now flow into our rotor magnets, and that means that stronger flux in there would actually create more CEMF in the stator winding. Now our applied voltage would still be the same, and so here's what would happen. Let me just take and show you. I'm going to extend this shape, this parallelogram, because remember, the line voltage is still the same. I'm just going to move this up here like this. Now at the point where this crosses that axis, this will be where the resultant voltage winds up. And so here's what I'd like to show you. If I take the rheostat, I reduce the resistance, which increases field current, which increases CEMF. This CEMF will rise to this level up here. Okay, so we now have CEMF up here. And here's what happens. And watch carefully, I'm going to completely erase these two lines out of here because they are going to, or not completely, I'll leave a little trace of them so you can see where they were. Okay? These two values here are going to change. Now what are those two things? Well, it's the net voltage and the line current. Now, because I have a greater CEMF, the addition of the line voltage and the CEMF inside of the stator winding now produces a net voltage that sits right here at 90 degrees. Like that. Okay? So that actually moves.
Now, where does the line current go to? Well, remember, it's going to ride pretty much just 90 degrees from the net voltage, or the resultant voltage. And look at what I have now for a line current angle. Now, the relationship, power factor is always the relationship between the line voltage and the line current. And here we have a power factor which equals 1. So this motor, what we do, the way it operates is we load the motor until we have kind of a pretty steady torque angle. So the motor is loaded to the angle that you're going to use it at. And then we take the field rheostat and we adjust it until we get a unity power factor. Now that unity power factor can be done, of course, you can check it with a power factor meter, but you can also tell if you adjust your field rheostat, and let's just say you had a current of, let's say you had a current of 25 amps, and you adjust it, you increase the resistance, and that current comes down to 20 amps. And then if you continued with more voltage, if you made this voltage even larger, then the net voltage would actually start to lead, and this current would actually come up and start leading. But the interesting thing is, if you started down here at 25, and then when you got to unity it was 20, and then when you started moving this way, all of a sudden it would go up again. So in other words, it would go, say, 25, down to 20, and then up to 25 again if you raised it up to here. And so what happens is the lowest current that this motor will draw, if you adjust that back and forth, for a certain load where the torque angle is at a certain point, the lowest current will always be when you adjust it to unity power factor. And think about it, at that point all you're delivering is pure resistive power, no reactive power. And so that's the lowest value that you can get for the FLA of the motor. And this is how they operate them. These are extremely efficient motors, and you can adjust them to run at a unity power factor. I just want to summarize just the different conditions then that we could have with this motor, just in terms of its power factor and kind of voltage and current relationships. So here's the pieces we have to work with. Essentially, you're always going to have your resultant voltage, and it'll be pretty much at 90 degrees to the line current. And our E line, which is always expressed right here on the x-axis at 0 degrees, and the CEMF, which changes its angle depending on how much load there is on the motor. And that, of course, is determined by the torque angle. Now, what I'm going to do is I want to draw an example here, and then I'm just going to modify it in a couple of different ways so that you can see what happens when, for instance, you just add a little bit of load, you take a little bit of load away, or what would happen if you just overexcite, which is what we call increasing the field current, overexciting, or what happens if you just underexcite at a given load. And so let's just take a look and let me show you. So first of all, we would start this motor, we would apply line voltage like this, and there's my E line. And then what I would do is I'm going to put a little bit of load, not too much, just a little bit. And here is my CEMF. And this, of course, the amount of CEMF when you start out is determined by the amount of field current. And so they typically adjust it so that, you've got a field current that's in the range, a similar value to the E line. Now, what you do is once you have the motor running and its line current is being drawn, now let me show you where the line current would be, and it should look about like this. I'm going to make that parallel to there if I can. This would be about at this angle. that. And so I can see that at this point, my net voltage sits right about there. And that means that this down here is going to be my I line. And as you can see, at this point, the power factor of this motor, the relationship between the line current and the line voltage, it's actually lagging, right? The current is lagging quite a bit. And so the first thing that we want to do in this situation is we want to increase our field rheostat and bring the motor to unity. And this is part of the normal adjustment that you would do as you're bringing it up and adding load. So let me do this. I'm going to put on some additional field current. We call this overexciting. And the way that I'm going to tell whether I've gone far enough is I'm going to extend this line across to there. Now that looks about good right there. So what I'm going to do is I'm going to increase, and this portion right here we would call overexciting. And we adjust it, and what this does is it now, this is where our net voltage and our line current were. Now it's up here. And my line current is now here at unity, okay? Line current at unity. Now, from this position, this is where it would normally run. And so there are essentially 4 things that we could do, and I want to explain what happens. And the first 2 things that we could do would be to add load, which would make this torque angle higher, or we could take away load, and that would make this torque angle lower. And so what we want to see is, if we were to add load, what would happen? Well, this torque angle would increase. And what that means is, let me just extend the lines a little bit so you can kind of get an idea. This would kind of go like this. Something like that. And then I need to change the angle of this one. And what would happen now is, between here and here, this net would kind of go up into here somewhere like that, okay? And that means it would actually be becoming more lagging. So in other words, it moves in the direction of lagging current, because if this moves this way, my current begins to lag. So really what I could say then is this lowers the power factor. Okay, because unity is the highest power factor that we can get. So by adding load, it actually lowers the power factor and it starts to lag. What would happen if we were to actually, when we're running at this point, now I'll get rid of all these little extra lines I made. If we're running right here, like that, everything's adjusted, we're at unity, what would happen if we suddenly reduce the load? Well, this line would move now down into this area, like this. And that would make this shallower, and my net voltage would actually come this way. It would actually come this way, like this. And that would make my line current move from unity up into a leading position. Now at that point, this motor would literally be delivering leading VARs into the line, or acting exactly like a capacitor. And so when you reduce load, if you're set operating at an adjusted point and you reduce the load, then what you're going to actually have is you're going to go to a leading power factor. Leading power factor. Now the other 2 things that you can do are, you can add CEMF, which we call overexciting, or you can lower the CEMF. And you do that, of course, by reducing the field current. And we call this underexciting. Underexciting. Now, if you overexcite, that means making this line even longer. And what happens is, for any given position, if I take, I'm going to go back to my unity position here, okay? So if I'm sitting at unity and I overexcite even more, and I bring this up here, that means that my net voltage will move a little bit further from 90 to say 100 degrees, and that means that my line current will become more leading. So for this one, this actually turns into a leading power factor. Okay, so if you're at an adjusted point in the middle, you add CEMF or you overexcite, you will actually create a leading power factor, and you're going to start producing some leading VARs, okay? Now, if you underexcite, that means this line's going to get smaller, the net is going to move in this direction, and your line current is going to move down, and this is going to become more lagging. So underexciting creates a, basically more lagging. So it moves from unity and it becomes lagging. All right, so just so you can see what the effect is. The main thing really is, if you're at a certain point and without making any other changes, you decrease the load, well, then what's going to happen is you're actually going to start producing some leading current. If you increase the load, well, then your current is going to become more lagging. And if it's overexciting, that's going to make it more leading. And if it's underexciting, that's going to make it more lagging. And so once you have that firmly in mind, now we can talk about the last sort of interesting application, and it looks like this. What would happen if we had a motor and here was the applied voltage right here, and the CEMF, we make lots of CEMF and it goes over here like this. Now it's very unusual that's it exactly at 180 degrees. It's usually a little bit of an angle just because of the there's always a little bit of torque required just to turn the rotor. So if we have this right here, what we would say then is our net at this point would probably be pretty close to, let me see, this is, I'm guessing if I drew this out like this, and then I drew this out at this same angle, I think that the net is literally going to be already like this. The net is actually leading a little bit. Now what this means is, if you take a look, this is a very small torque angle. And so here's what they do. They take a motor and they may place a small load on it, or they may actually place virtually no load on it. And what they do is they just play with this. Overexciting. Now it goes at the same angle. Whatever the torque angle is, this voltage just extends further at the same angle, right? And what you do is, as you overexcite this, this angle becomes further and further in this direction. And that means that your current that may start here can actually go into these areas up here. And so what they do is they take this motor, they may use a little bit of its ability for mechanical load, but for the most part, they actually utilize this leading current to correct power factor. They'll hook this synchronous motor up on an MCC with a group of other motors that all have lagging power factors, and this motor will actually correct the power factor for all the other motors. And in some cases, they actually produce a motor, looks like this, and it doesn't actually even have an output shaft on it. It's a synchronous motor, the rotor's in there, they hook it up and they run it. And they don't even want the mechanical output. all they use it for is to produce leading VARs, and they'll take banks of these in the thousands of horsepower, and they'll produce just huge amounts of leading VARs, for instance, to correct, like high voltage transmission line for the power factor on those type of lines. So what they'll, the interesting thing with that type of a setup is all you have to do to change the amount of VARs that one of these is producing is vary the field current. And so it's not like a capacitors where you have banks of capacitors and you kind of have to add them with contactors in groups. This is completely adjustable, and so as the power factor rises and falls on, say, a high voltage transmission line, you can read that in real time, send your inputs to the PLC, and it then adjusts the amount of field current going to the asynchronous condenser. We don't even call it a motor at that point, and it adjusts its output of leading VARs to actually change and correct the power factor in real time. So just an amazing piece of equipment. A motor, we can use it as a capacitor. Oh, and how would we use this as an alternator? Let me show you this. I'm just going to show you the vectors first. If you take this machine, remember, we used to have this, but now all we have is a machine and we're driving it with a prime mover. So that means that the rotor is spinning at a very constant speed, and we energize our field switch, so now we have flux in there. Now the interesting thing is there a revolving field? Well, no, actually there is no revolving field because we didn't apply any line voltage. So what we have is simply, we're taking a prime mover and spinning the rotor of this machine, and now we energize these magnets that we have on here, and all of a sudden we have flux around these magnets. And this flux is spinning around and cutting across these stator windings. Now what happened when the flux cut the stator windings in a synchronous motor? Well, we produced this, and we called it CEMF, and it balanced against our line voltage. Well, guess what? We no longer have line voltage, so what we really are doing is we're just taking a prime mover, we're spinning the rotor, energizing the field, and this now becomes our three-phase output voltage. And that's about as complicated as that is right there. Okay? So, motor, capacitor, and a three-phase alternator.